Okay, we're going to be doing lead code 116, populating next right pointers in each node. So this is, if you've done binary tree level order traversal, this should be easier, but can be a bit tricky, but it's not. So you're given a perfect binary tree, which is, by perfect, it means it's filled at every level from left to right for all levels. No gaps, no gaps in it. Where all leaves are on the same level and every parent has two children, right? So the binary tree has the following definition. It has a variable, it has a pointer to the left, which stores the left child, a pointer to the right, which stores the right child, and a third pointer called next, right? So you populate each next pointer to point to its next node. If there is no next right node, the next pointer should be set to null. Initially, all next pointers are set to null. This is very key. All next pointers are set to null. So this is set to null. So this is the figure for what it is before, and this is the figure for what they want it to be after. But this is not a correct illustration. And let me show you what the correct illustration is based off the question. The correct illustration is this. Null, 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 null. Right? So this is exactly how it is. Not this. Not this. Right? So the next thing we're going to do is I'm going to show you how we solve it. Okay, the other thing that you need to consider is that if the root is empty, then we're simply going to return the root itself, right? So let me type that up actually here. So in other edge cases, we are doing something like if root is none, then we would return 0 if it's like, if the return type was supposed to be an integer, or we'd return an empty array, right? But here, we want to return the tree itself, the empty tree, right? So that's how it is. This is the edge case. Very important that you do this right. So the solution to this algorithm, the algorithm to this problem is, we are going to use breadth first search, obviously, because we're going level by level, right? But the most important thing to solving this is simply, we maintain a queue, obviously, and then at each level, we instantiate a previous pointer, which is what I've represented here. And this previous pointer will grab whatever this is and adjust its position as we iterate through. So an illustration is the best way to show this. So let's start with this, right? So we're going level by level. So we're at the first level, we initialize our queue to 1, right? And then what's the next thing after initializing? We have, this is the length of our first level, so we pop it off, right? When we pop it off, we check if it has child nodes. Yes, it does, because in any case, it's a perfect tree and we're not at a leaf. So then we add these to the queue, right? So we have created the next level for the queue. So here we have 2 and 3. So after we're done doing this, right? After we're done doing this, we set initial at every level. We have to start out by initializing our previous to none, right? And then after that, we pop off the, obviously we pop off the level as I showed you. We add these two, and then if the previous is not none, we set its next pointer to the next node. I mean to the current node, right? Otherwise, if previous was none, we set it to this current node. So I push this node here, right? So I'm going to stop here, and then I'm going to do the algorithm so that you see it, right? And then we can come back and continue here, right? So bear with me, we're going to come back to this. So we initialize our queue. Q is equal to collections.dq, which is root, and then while q, that means it's not empty, we get the num nodes, because we want to know how many are at this level. So num nodes is equal to length of q, and then we instantiate our previous pointer for this level. This previous pointer will reassign for all nodes at this level, i.e. set them to the next pointer, right? So we initialize our previous with none. So now we're going to go through the level. For I in range, num nodes, we pop off, so node is equal to, so for example with the 1, since it's the only one at this level, we're going to iterate through once, so node is equal to q dot pop left, which is what we did. And then when we came here, we populate the rest of we populate the queue with new nodes. So if node.left is not none, guess what? Q.append node.left. Then if node.right is not none, q.append node.right. Okay. So now we adjust using the previous pointer. And how do we do this? If previous is not none, that means it contains, if previous contains a node, then we set previous dot next to the current node we're at, right? So if we go back to this, here previous is none, right? So we don't do anything, right? But then remember we had popped off this, so we're like, is previous, so we're like, if previous is not none, doesn't run in this case. So what runs is the next code, which is previous is equal to node. So now we set our node to, we now set this to, we now set our previous to the current node we are at, right? And then this while loop for the root node, it's only iterating through once, so it will end here, right? So this is the whole code. This is the code that's going to happen, and here we'll simply return the root because all of them will be in the right places. So now we're going to continue on with this code and our diagram, right? So let me adjust this so that we can get a better view. So we're going to go to, all right, so that's perfect. So we're now at this level and we're back here, right? So Q has Q is still filled with these values. Sorry, Q is still filled with these values. So we're going to go to get the num nodes. Let me put here num nodes. Num nodes is now 2, so we're going to iterate through twice, right? Num nodes is 2, we're going to iterate through twice. We set, remember, this is a new level, so we're just reinstantiating our previous to none. The one that we had set it to before was knocked off. So we come here for I in range 0 to 1. So we pop off the node, right? Which is this. We pop it off right here. And then we ask ourselves, if node.left is not none, node.left has this, node.right has this. So we're appending those two to our array, right? So the three most closer to this side, and then we have 4 and 5, right? So we come back to our code. We're now here, right? So if previous is not none, do this. But look at the diagram. Previous is actually none, so this code doesn't execute. So we set our previous to the current node. So it comes here, right? Then we come back all the way up here to the next iteration. We knock off 3. So when we knock off 3, our 4 and 5 come this side. And then we now ask ourselves, does 3 have a left and right? Does it have children on the left and right? Look at the diagram. Yes, it does, here and here. So we're adding 6 and 7 to our queue. 6 and 7, right? So then we come down here. If previous is not none, so look at the diagram. Is previous not none? Yes, it's not none. So we set our previous. We set it to this current node we're at. This one. You see that? So then that means here, when you look at the perfect tree, right here, look at the perfect tree. This was pointing to null, but now it's going to be pointing to 3, right? So now that we're done with that, we're done with this level, right? Because we only had to iterate through twice. We're now done with this level, and we're going to go all the way back to while q, right? So that means that this is going to get knocked off the previous, and the previous is actually doesn't exist anymore. So we come back here, we get the num nodes, right? The level at this, the number of nodes at this level. Notice that it's increased. It's now 4. So our num nodes is now 4, right? So we're going to iterate through 4 times. So the first thing we do is we initialize our previous. We instantiate and initialize previous to none. And then we pop off. We're going to iterate through 4 times. Look at the code. We pop this off. Just the 4. Okay. And then if node.left is not none, look at the diagram, look here. Guess what? This is for all these remaining, these are leaf nodes at this level. So all these, so this code here isn't going to run for all the leaf nodes, right? So all that's going to run is this. So we're now at 4. If previous is not none, previous.next is equal to none. But let's look at our previous. In the diagram, our previous is currently set to none. So the code that will execute is previous is equal to our current node, which is this. So we move it here. Then we come back here. We pop off the 5, right? Look at the diagram, we pop off the 5, it comes here. 5 is a leaf node, so this code here won't run. This code, let's see if it will run, this one. If previous is not none, let's look at our previous. Yes, our previous is not none, so previous.next is gonna point to this. So we adjust our diagram here to show that it's now pointing to 5. Okay. And then we come back all the way here. This node is so previous.next. Then after that, we have to set our previous. After we're out of there, our previous has to be set to the node, right? So that we can move previous forward. So this comes all the way here. We can eliminate this and just have this. So now our previous is pointing at 5. We come back here, we come back to this code, and then we pop off the queue. We get a 6, it comes down here. This code doesn't run because, I mean, it runs, but it doesn't execute the internal statements because 6 is a leaf node. We come back. If previous is not none, set previous dot next to node. So previous is obviously not none. So this points to our current node. And let's adjust our tree to show that. You can see it here, right? And then after we're done with this code, we set our previous is now equal to the current node. So this comes all the way here, and then this disappears. All right. So then we come back here to our last iteration. We come back to the for loop, our last iteration. So we knock this node off. Oops, hold on. Okay, we knock that node off. This code doesn't execute. And then what executes is this. If previous is not none, right? And yes, previous is not none. We set previous to this. And then let's illustrate it here. And then we set our previous to node. Right? So then this iteration is done. And then when we come back to the while loop, guess what? While q, but q is empty. If you look here on the diagram, q is now empty. So we're just going to execute return root and look at our tree. Voila, it's solved. So the runtime complexity for this is O of n, and the space complexity is also O of n, right? Because even though we may be getting like a fraction of n, it's still n, right? So yeah, that's the solution to populating next right pointers in binary tree. Thank you.